Okay, we will start. So, hello everyone. Welcome to Network Seminar Series hosted by the Center for Network Intelligence at the EC and RBC CPS IASC. It is my pleasure to introduce today's speaker, Professor Nikhil Karamchandani. He will be speaking on group testing, something old, something new, something borrowed. Professor Nikhil is an associate professor with the Department of Electrical Engineering, IIT Bombay. He received a PhD degree from the Department of Electrical and Computer Engineering, University of California at San Diego. He was a postdoctoral scholar with the University of California at Los Angeles and the Information Theory and Application Center, University of California at San Diego. His research interests include networks, information and coding theory, and statistical learning. We request the audience to keep your microphone silent for the duration of the talk, except when asking questions. And for questions, feel free to unmute yourself and ask directly or type them in the chat box and we will relay your questions. Over to you, Professor.
Right. Thanks, Srishma, for the production, and thank you for the invite. I'm sorry I couldn't make the trip to ISC this time. Hopefully next time. Can you confirm that my slides are visible to you?
Yes, it's visible.
Okay. Okay. Like the title suggests, I'm going to talk about this problem of group testing. I'm going to talk about some old well-known results and some new variant and results that we've been considering recently. So some of you might have been at Siddharth's talk yesterday. I was there, and so some of this might be a little bit of a repetition, but one key difference from, let's say, what Siddharth talked about yesterday to today is I'm going to focus more on the zero error combinatorial setting, whereas Siddharth talked more about the recovery with vanishing error. So we'll see this as we go along. Okay, so just some introduction about the origin of the problem. So this group testing problem was first studied by a scientist, Robert. And this was mainly concerned with syphilis testing among soldiers who were returning from the World War. And of course, one possibility for such testing was individually testing each soldier, but that would have been inefficient since you would require a large number of tests, and most of the people were not infected, so most of the tests would in fact just turn out to be negative. So the idea was, can we somehow pool samples from multiple soldiers together and test them together? And if so, if you get a negative test, then you immediately know that everyone in the pool is uninfected. And if you have a positive test, then you know that there is at least one soldier in that particular pool who was infected. So it gives you a more efficient way of testing in this kind of a scenario. And the goal was to design pooling strategies which minimize the overall number of tests that are needed. So the history is essentially, or the problem came about from an application in disease testing, but since then it has found applications. This problem of group testing has found applications in all kinds of areas, ranging from quality testing in industrial applications to network tomography, something we're going to talk about a little later, where you want to kind of figure out some congested edges in a network using certain probes, or neighbor discovery in wireless networks, genetic screening in DNA sequencing, etc. So anywhere where you have like a big population and there is some small subpopulation which is of interest, and you can somehow design a test which can pool together multiple of them together, all of those applications are scenarios where group testing can find an application. Okay, so how do we model this kind of a problem? So just setting up some notation. So we have some n items, and amongst these n items, we have some unknown subset of, we're going to call them defectives. and we're going to denote that subset by calligraphic K. And all we know is that the size of this set is at most K. Okay, and we're going to think of this K as being much, much smaller than the overall population size. Now, I can represent each test that I conduct by a binary n-length vector, okay, where if I have a 1 in a certain position, let's say the ith position, then that means that item I is included in that particular test. So in this particular example, if you see, the first 4 items are included in this test and the last 4 are excluded in the test. And here, for example, the items in dark are supposed to be the defectives. Of course, we don't know this a priori, but these are the 2 defectives amongst these 8 items. So if I conduct a test of this kind, what is my output or what is the outcome of the test? So the outcome of the test is positive if amongst the items that were included in the test, there is at least one defective item. Okay, so this can be written in this particular form here, which is just the kind of the Boolean OR over all the elements in the true defective set, right? So if even one of these items in the defective set was included in the test, then the outcome will be, let's say, 1 or positive. And if none of the defective items were included in the test, then the outcome of the test is going to be negative. Now, we can now stack together multiple such tests, right? So, for example, if you look at this third test, only the first 2 items are included in the test, and both of those items are not defective. So the outcome turned out to be negative. Other tests outcome turned out to be positive. So you can stack them all together in this kind of a test design, which is like a binary matrix with capital T rows, T being the number of tests and N being the number of columns or the number of items. The output is just going to be like row-wise XOR. So Xi can be thought of as like the ith column of this matrix. And then for every row, you are taking this Boolean OR. So that's how you get the output of all the tests. Now we say that such a design is feasible if we can recover any possible defective set by looking at the outcome of the tests. Okay, so we don't know this set of defectives beforehand. All we know is that the number of defectives is at most this number K. And somehow we want to look at the outcomes of all the tests, and we want to recover our underlying subset of defective items. So if that is possible, then we say that this testing design that we have come up with is a feasible design. And our goal is that given these parameters N and K, N being the population size, K being the upper bound on the number of defectives, we want to find feasible testing designs of minimum size. And secondly, we also want to come up with explicit constructions of these testing designs and also efficient decoding rules. So that's broadly the goal in group testing. Now, what does a feasible testing design mean here, right? So if you have a feasible testing design, then as I said, no matter what the underlying defective set was, you should be able to just look at the outcome of the tests and recover from them the original defective set. So that immediately implies that there has to be a one-to-one map between the set of possible defective sets and the set of possible outcomes, right? So that immediately gives us this inequality. We have, if you look at the space of outcomes, right, there are T binary outcomes if you have T tests. So the number of possibilities for the output vector is 2 to the power T, right? So you want to have enough number of output vectors such that it has to certainly be larger than the number of possible defective sets for any feasible testing design, which is why you have this particular inequality, which immediately tells us that the number of tests for any feasible testing design has to be at least of the order of K log N by K. So this immediately gives us a lower bound on the number of tests that the best possible number of tests that we can hope for in this problem. Now, how can we come close to this lower bound? What are some achievable strategies? Okay, so let's talk about that next. So there are broadly two classes of uh, design strategies that people have looked at. One is adaptive testing, where you can design the tests sequentially. So what does that mean? That means that I can, at any given point, I can design the test after looking at the output or the outcome of the previous tests. So it gives me this kind of flexibility that I don't have to predefine all my tests. At any given time, I can look at what the outcome of the previous test was and then design my test. So let's look at what one can do if you have the ability to do adaptive testing. Let's look at the simple case where there is just one defective item. Okay. So as you would imagine, if you give it a little bit of thought, one possibility for when you are allowed to do adaptive testing is to just conduct kind of a binary search. So you start with your entire, you have n items, right? You split them into two equal halves, and then you test each of them, because there is only at most one defective item. So you can at most have one of these halves will give you a positive outcome. So if, let's say, the second half gives you the positive outcome, then you just focus on that and remove the remaining items, and then you keep going on, keep doing this. So at each time, you are essentially removing half of the items. And so you can easily see that in this particular case, you will require at most log n tests to recover the defective item. Okay. Now, what if the number of possible defectives is more than one? And one easy thing to do is to just repeat the above process. So you just keep doing this process till you identify one defective in a particular round. You remove that defective, and then you repeat the same process again and again. So you're doing this binary search repeatedly, and in each kind of iteration of this, or each round of this binary search, you're guaranteed that you will remove at least one defective item. And if you do that, so you will have to at most repeat this same process k times. So you require at most k log n tests. Now, of course, I think you can easily see that this is not the most efficient way of doing that. And it turns out you can actually do something more sophisticated, which is called generalized binary splitting. And that, in fact, achieves order k log n by k tests. So you improve from k log n to k log n by k. And furthermore, this is in fact order optimal with respect to the lower bound that we had seen before, right? So this tells you that, okay, if you're looking for adaptive testing, meaning you want to, your application allows you to design tests sequentially, then in fact you can achieve this information theoretic lower bound of k log n by k. Okay. So this is just a table which just illustrates what we just saw. You have, in the adaptive case, things are pretty much clear up to at least constant factors. Now, what happens in non-adaptive testing? So in non-adaptive testing, your testing design matrix has to be specified beforehand. So all the tests that you're going to conduct have to be pre-decided. You cannot design tests sequentially anymore. And the idea or the motivation for doing something like this is to allow parallelism. So you want to be able to do these tests in parallel. There are several applications where you can't wait for things to happen sequentially. You want to quickly do these things, and so you want them to happen in parallel. So now we can't do kind of a binary search type of a procedure. So in this particular case, there is this combinatorial notion that becomes useful, which is called disjunctness of a matrix. So let me define what I mean by a T-disjunct matrix. So a T-disjunct matrix signifies that the union of any T columns does not contain any other single column. Okay. So let's look at an example. So we have here a 6 cross 4 matrix, it turns out that this matrix is in fact two disjunct, which means that if I take any two columns, then that the union of those two columns or the Boolean OR of those two columns does not cover any other column. So for example, if you look at the first two columns, and you look at this third column, right? So you take the union of these two columns. By the union of these two columns, I mean the union is going to be one if either one in, let's say, any position, if either of the two entries corresponding to column 1 or column 2 is 1. So you can notice that if you look at this entry here, in the fourth row, right, then both these columns have a 0 there, whereas our entry in the blue in the third column is a 1. So clearly this is these two columns do not contain the third column. Similarly, if you look at the fourth column, then again you can see that the first two columns are 0 and the fourth column also has a 1 in the fourth position. So again, this fourth column is also not covered by the union of the first two columns. Okay, so this matrix is indeed, I mean, you can verify for all other pairs as well, and it turns out that this matrix is indeed two disjunct. Furthermore, this matrix is not three disjunct, and the way to see that, or one way to see that, would be that the union of these three columns, the last three columns, in fact, cover the first column completely. Right. So it turns out that this is not a three disjunct matrix. So this is what we mean by T disjunctness. Now, this combinatorial notion of disjunctness turns out to be very, very closely related to the ability of, or the feasibility of, a testing design matrix. So it turns out that if I have a feasible testing design matrix which can deal with up to k defectives, then that matrix has to necessarily be k-1 disjunct. And similarly, the opposite direction also holds true, which means that if I take any k disjunct matrix, binary matrix, then that immediately gives me a feasible testing design matrix. Okay, so I'm not going to do the forward part, but I'll just try to illustrate the reverse direction here, because that gives us a way of constructing feasible testing design matrices. So it's saying that if you can come up with a k disjunct matrix, then you immediately have a feasible testing design which can deal with up to k defectives. So just again via this example of 6x4 two disjunct matrix that we have, let's say we want to deal with up to two defectives, and we know that this matrix that we have here, right, it's a two disjunct matrix. So k is equal to 2. Now we want to see whether this matrix can in fact recover any pair of defectives. Okay, let's say just assume, let's say that the unknown set of defectives is in fact item 1 and item 2, which means that when I run all these tests, the output that I'm going to get is going to be exactly the Boolean OR of these two columns, the first and the second column, or the union of these two columns. Okay. Now, because the matrix is two disjunct, so I know that the third column is not going to be contained in the union of the first two columns. So it's not going to be contained in the outcome vector, right? What does that mean? That means that there is at least one test, okay, or there is at least one row where this third item, which is in fact a non-defective item, right? That item is present and none of the defective items is present. So the outcome of that test is going to be 0, and I will immediately know that this particular third item is in fact a non-defective. So you can think of this as being like a witness test for item 3, for the non-defectiveness of item 3. Okay, and this is happening because the matrix is in fact disjunct. So there is going to be at least one such test. Similarly, for the next item, which is item 4, which is again non-defective, again the same test is going to be one where the item 4 is present and none of the defective items is present. So again, this test is a witness for the non-defectiveness of this particular item. So in general, this holds true more generally as well. Beyond this example, you will always have this property of k disjunctness guarantees that for any non-defective item, there will be at least one test which can immediately establish the non-defectiveness of that item, which means that that item is going to be present in the test and none of the defective items are going to be present in the test. Okay, so that's why this disjunctness relates so closely with the feasibility to identify defectives. And furthermore, it also gives us a very simple decoding algorithm. So if your underlying testing design matrix is disjunct, then all you have to do is you look at any particular item, and if all tests involving that item are positive, then you mark it as defective. Otherwise, you keep it as non-defective. Okay, so it also suggests a simple decoding algorithm. So this notion, the main point I'm trying to make here is that for non-adaptive testing strategies, we have this combinatorial notion of a disjunctness of a matrix, and that plays a very crucial role in establishing feasibility and coming up with constructions, etc. So in fact, this notion also leads to lower bounds, or has led to lower bounds uh, on the number of tests that are needed for any non-adaptive testing strategy. So this so we have a particular lower bound which says that you require at least k square log n tests to recover up to k defectives. And this comes up by essentially utilizing this connection to disjunctness and also what are called k-cover families in graph theory. So notice that you are required to pay a penalty of at least a factor of k if you go from adaptive to non-adaptive testing. And then people have come up with various constructions as well, which come close to these lower bounds. So if you just do a random construction where you choose every entry kind of Bernoulli with some probability, then you can come close to this upper bound. And this is close to some of the constructions that Siddharth talked about yesterday as well. And there are also explicit non-randomized constructions. In particular, one of them, one classical one is one which is based on the idea of concatenated codes. It concatenates, I think, a Reed-Solomon code, and again, inside the inner code is a one-hot code, I think. And so that concatenation gives you again, so it kind of relates this notion of codes to the notion of feasible design matrices. Okay, and it gets you somewhere close to the upper bound, sorry, to the lower bound, which is of the kind of the order of k square log n. Okay, so overall we have this particular picture. So our the standard Boolean group testing problem, right, where every test is like you can select some subset of items, and the outcome of the test is positive if at least one defective item is selected in the test. Otherwise, the outcome is negative. So what we've seen is that in the adaptive scenario, your upper bound and lower bound are both of the order of k log n by k. And in the non-adaptive case, you do have to pay a penalty of a factor, at least a factor of k. And your lower bound is of the order of k square log n, and the upper bound again is of the order of k square log n. Okay? But there is some small gap. As far as I know, there is still some small gap there in the general problem. Okay. So this is kind of the standard or classical group testing problem. So if you one kind of point I want to make here is just for people who might have attended Siddharth's talk yesterday. You might notice here that in the non-adaptive case, we have a k square log n, whereas what he had was a k log n, and the difference is exactly coming from the fact that our criterion is stronger. We require zero error or perfect recovery, whereas the criterion that Siddharth was talking about was allowed for some vanishing error probability. So that kind of relaxation of the error criterion knocks off that additional factor of k. Okay. So I'm going to now kind of move on forward. This is like history of what is kind of the classical group testing problem. If there are any questions at this point, then I can take them now. Otherwise, I'll move forward to some new model that we have been looking at. Okay, so this is like the most basic, I would say, vanilla problem formulation. People have, of course, looked at several variants of this problem, starting from, of course, the error criteria, as I said, the recovery criterion itself, whether you ask for perfect recovery or you ask for partial recovery and so on, or noise in the model. Also, there have been several works which look at kind of different kinds of tests. So going beyond just Boolean tests. So there are testing strategies like threshold testing, quantitative testing, which look at testing strategies which give you more than just the Boolean information that the standard group test gives you. Okay. And in some recent work, we've also looked at one such situation where a particular test gives you information beyond what a Boolean group test gives you. Okay, and this was joint work with Vakar, who was an undergraduate student at IIT Bombay. Is now a grad student at Caltech, and Niranjan, who's a colleague in the math department at IIT Bombay. Okay, so the motivation for us, or one of the motivations was this problem of network tomography that I mentioned. So this problem of network tomography is one of the applications of this idea of group testing, and the setting is that you have some underlying network, and there are some particular congested links in this network, which are denoted by the red here, right? And you want to identify these congested links in the network, and the test corresponds to sending a probe packet across this network. So, for example, you might send a probe packet from starting from 1 along this path of 1 to 2, 2 to 3, 3 to 4, and 4 to 7, right? And in the standard binary group test, what such a probe will tell you is that if it encounters any congested edge, then the probe will return a positive, and if it does not encounter any congested edge and it reaches the designated sender, then the test outcome will be negative, which means that all the edges on the corresponding path were congestion free, right? Now, so here the outcome in when group testing was when standard Boolean group testing is applied to such a problem, the outcome is binary. It's either a positive, which indicates the existence of a congested edge on that path, or negative, which tells you that all the edges on that path are congestion free. Now, there are protocols which actually give you more information than just that. In particular, there are in fact protocols where the packet, when it passes through the network, if it encounters an edge which is broken or a link which is broken, it comes back to the sender with the information of the first broken link that it encountered. Okay, so the idea is in for example, this particular path, the outcome of the test would not just be a yes or a no. It would, in fact, the packet will traverse this path. It will then encounter this congested link 3,4, and it will return to the sender saying the link 3,4 was the first congested link that I encountered. Okay, so it's giving you more information than just Boolean. It's giving you the identity of the first defective item that it encountered in the test. Similar kind of situation also occurs in recommendation systems. For example, think of a scenario where a system is recommending various, let's say, news items related to various topics to a particular user, and it's trying to learn which topics amongst a large collection of topics is the user interested in. So again, you have like a list, and the user goes through the list, and the first link that it clicks tells you the identity of the first, again, so-called defective here, but it's the first kind of interesting topic that the user found, right? So again, it gives you more information than just Boolean yes, no. It's telling you in that sequence of test, what was the first item of interest that the user found, right? In fact, some problems of this kind of a feedback structure has also been studied in sequential learning frameworks like Cascaded Bandits and the online learning to rank frameworks. And that's also where some of our motivation came from. So how do I model this kind of additional feedback that I'm getting beyond the classical Boolean feedback? So we again go back to our setting where we have n items, and again there is some unknown subset of defectives with size at most k, right? Now each test in this particular testing framework is going to be an ordered subset of items. Okay, so in, let's say, if T1 was 3, 1, 5, 7, then that's like an ordered subset of items. And the outcome of the test is going to be the first defective item in that sequence. So in this particular case, where the underlying, let's say, defectives were 2 and 5, which we don't know a priori, the outcome of this test will be 5, because that is in this order, it is the first defective item that was encountered, right? Similarly, if the test sequence was 1, 2, 3, 4, 5, 6, then the outcome will be 2, because that is the first defective outcome, sorry, the first defective item that is encountered in this test, and so on. And if you have a test where there are no defective items at all, then the outcome we'll assume the outcome to be just 0. Okay. So this is kind of the testing framework that we have, and you can see how it relates to the applications that I mentioned in network tomography and recommendation systems. So again, like before, we can talk about testing design, which is like a collection of tests. So now a collection of tests is just a collection of ordered subsequences, right? And the output is again a vector which corresponds to the first defective item encountered in each such ordered subsequence. Okay, and again, we are going to say that such a testing design is feasible if we can recover any underlying collection of defective items, as long as their number is at most small k. And the goal is the same. We want to find feasible testing designs of minimum size, which means we want to come up with collections of such ordered subsequences, the smallest collection of ordered subsequences, which allows us to recover the identity of the defective items. As before, we want to come up with explicit constructions and efficient decoding rules. Okay, so I hope the model is clear. Yeah, I can take any questions if there are about the model. Okay, so now let's compare how this testing framework is different from the standard binary group test. Parimal, go ahead.
Hi, it's actually Siddharth.
Yeah, hi, Siddharth.
So the two motivations you had, tomography and user recommendation. So the tomography setting, the graph structure itself imposes some constraints, and sometimes that can be the dominating factor rather than like more classical things, right? Because you can't test arbitrary subsets.
No, I completely, that's completely true. Yeah, we're starting from like the simplest possible setting here. But I agree. Yeah, I mean, in an actual application of network tomography, that is certainly something that has to be taken into account. Yeah, we are starting from.
And the recommendation systems thing, the user will basically just sequentially answer these things. So again, it seems like adaptive is the more relevant thing over there. My basic context is if there are motivating examples that are geared towards your most interesting results, which are non-adaptive, general.
Yeah. So again, I mean, I think again, yeah. So one would it depends on what the setting is. For example, in an online, in the recommendation system setting, again, it depends on what kind of a situation you are in, right? Do you want to send one set of questions to the user and then wait for their answer, then send another user, another, let's say, list, and then wait for their answer? Or do you want to give them a bunch of tests, one-shot tests in one go, and not wait for them and then just give them the answer?
Okay, I see.
So I think, yeah, I think one can come up with scenarios where you, in even this context of recommendation systems, you don't want to do this really sequentially, because that might just be too slow a process.
Okay, thanks.
Yeah. Okay. So how does these two kind of testing frameworks compare against each other? So if I ran the same kind of tests in the standard Boolean
Nikhil, you're mute.
Sorry, yeah, am I audible?
Yes, yes.
And my screen is visible. I think I lost my connection briefly.
Okay. And not yet. The screen is not visible yet.
Okay. Me maybe reshare.
Okay.
How about now?
That's visible. We can.
All right. Okay. So yeah, as I was saying, so if you have any feasible testing design under the binary or the Boolean group testing model, then also that gives you an immediate feasible design under the cascaded model as well. So any upper bounds that we saw for Boolean group testing are definitely upper bounds for the cascaded group testing model as well, right? So you immediately get upper bounds from the prior results. The main question that we are interested in is how much can this additional information help, and in what scenarios? Okay. So this is the original Boolean group testing results that we saw before, and all I'm saying here is that all the upper bounds that we had for Boolean group testing are immediate upper bounds for the cascaded group testing model as well. We want to see whether and how much can we improve upon these using the additional information that we are getting from a cascaded group test. Okay, so let's first start with kind of the adaptive testing model, which is kind of trivial in this cascaded setting, but I'll just go through it very quickly just to set up, just to kind of maybe set up some notation and also give you an idea of how this testing framework might be useful. So here in adaptive testing, you can sequentially design the tests, right? So it turns out that under this cascaded group testing model, it's very, very easy to to come up with optimal testing designs. So all you need to do is you just start with, let's say, all the items, okay, in the first subsequence or the first test. You run a test with that. So let's say in the first test, you just go from 1 to 7. So you will at least, if there is any defective remaining in the collection of items, then at least one defective will be caught in this test, right? So for example, if I do my first test as just the natural order 1, 2, 3, 4, 5, 6, 7, it will catch the defective 2. You remove that defective and you go back. You now run the same test after removing this item 2. Now you run 1, 3, 4, 5, 6, 7. Again, you are guaranteed to recover at least one defective item if there is any remaining. and so on, right? So because you're able to do this adaptively, you will require at most k tests to recover all the defective items. So this is just saying that in via this table. So all you have to do is just keep running this natural permutation and keep removing the items that you have recognized as defectives. So here it needs at most k tests, and it's also clear that you require at least k tests because in each test you can at most identify one defective item, right? So the adaptive setting is very simple. It's trivial in this case. Yeah, the main thing that you are getting out of this is, in fact, this cascaded group test is improving things from k log n in the Boolean group test to just k. So in the cascaded group test. Okay, so the adaptive setting is kind of trivial. Let's go to the non-adaptive setting, where now you have to kind of specify this collection of permutations beforehand. You can't design these permutations on the fly. Okay. So let's say we just have one defective item, right? So in this case, how many tests do I need? So you can easily see that only one test suffices. You just, if your first test itself is just the natural permutation and you know that there is at most one defective item, then just this natural permutation 1 to n will catch that defective item and identify it if there is any. So if k is equal to 1, then just one test suffices, right? What about k equals 2? What if there are at most two defectives? So yeah, maybe one can try and think a little bit about what collection of permutations or how many permutations do you need to specify to catch at most two defectives. So again, if you think a little bit, you can see that two tests actually suffice. So you just take one permutation to be the natural order 1 to n, and then the second permutation to just be the reverse. And you can see that if you have any two defectives, these two tests will always catch both the defectives. So for example, let's say if the defectives were items 2 and 5, then in the first test, you are going to go from 1, 2, 3, 4, and so on. So you will catch the smaller item index, which is 2. And then in the reverse test, you will encounter the larger item number, which was 5 before 2, right? So for any such pair, you will have one of these tests will catch exactly one of them, right? So again, two tests suffice to capture any pair of defective items, right? So it turns out, in fact, this is optimal, of course, for k equals 1 and k equals 2 as well. So you require just 1 and 2 tests in these case. And again, for comparison, recall that Boolean group testing would require order log n tests, right? So there is a dependence on the total number of items in Boolean group testing. And for k equals 1 and 2, you're getting this benefit because of the additional information that you're getting from each test. You're able to get a number of tests which is in fact independent of the underlying population size. So of course, the natural question is, what about larger values of k? And immediately, if you go to k equals 3, things start becoming a little more tricky. Okay, and it took us quite a while to figure out something better than standard group testing, even for k equals 3. So I'm going, before I go to the particular construction, I'll first kind of define again this notion of feasibility. So just like we had a notion of feasibility for standard Boolean group testing, right? That notion was disjunctness of a matrix, this combinatorial notion of disjunctness, which was related to the union of a certain number of columns not covering any other column, right? Similarly, under this cascaded group test, we can again come up with a notion of what a feasible testing or what the feasibility of a testing design needs. So as I said, we call a testing design to be feasible if we can recover any subset of defectives from just looking at the outcomes. So what we need is that if I have any two different subset of defectives, right, we should have then corresponding to those, we should have distinct output vectors. Right. So for example, let's say if my this was my collection of tests, right? And if the underlying defective set was 1, 2, 3, then you can see that my outcome will be 3, 1, 1, 3, 0. So if I look at, for example, the first test, the first defective item that is encountered is 3, so the outcome is 3. If you go to the second test, the first defective item is 1, and so again the outcome is 1, and so on. On the other hand, if the defective set was just 1, 3, okay, 2 was not a defective, the defective set was 1, 3, you can check that even in this case, the outcome vector would remain the same, okay? And that is because there is no test where 2 in fact comes before 1 and 3. So the only test where 2 in fact plays a role is test 2, but you can see that here 1 beats 2 because 1 appears before in the sequence. So you never get to see that 2 is actually defective. Okay, so this is not a feasible testing design because there are two different possible defective sets which both lead to the same outcome vector. Okay, so this is not a feasible testing design. So now we want to come up with, okay, what is a condition that I can put on the testing design matrix which will ensure feasibility. And so I want an analog of the disjunctness property. So here is the analog of the disjunctness property for cascaded group testing. So what you need is that you look at any subset of the population whose size is equal to the number of defectives k. And within that subset, for every item, there should be at least one test where that item V beats every other item, every other defective item. Okay, so let me repeat. I want to make sure that for every possible defective set, okay, so for every possible this set K, right, whose size is small k, I want to make sure that there is at least one test, right, which will identify every item in that set to be defective, right? Because for an item to be identified as defective, it has to come before all the remaining defectives. Okay, so this is the property, or this is the equivalent or the analog of the feasibility condition that we need any feasible testing design to satisfy. Okay, so if you so again for this testing design, if I go to k equals 1, 2, 3 like we did before, so you can see that this testing design v equals 1 has a test where it appears before 2 and 3. V equals 3 also has a test where it appears before 1 and 2, but corresponding to v equals 2, this particular item, I do not have a test which appears before the remaining two defectives. There's a question.
Yeah, so that again. So in classical group testing, there's disjunctness, but there's also separability, right? And they're closely related. Is there a similar thing happening here?
So I mean, yeah, there is. I don't know if there is another notion. So this is the notion that we at least have used for our constructions and our lower bounds. So, there might be other notions.
So disjunctness leads to very efficient decoding. Separability need not. Which of these two does this correspond to?
So as we'll see, I mean, the decoding rule here is quite simple and straightforward. So efficiency is not an issue as compared to decoding. So I don't know if there is, or at least we don't know of another, let's say, criteria or feasibility condition which gives us a different viewpoint. We haven't yet come across one.
Okay, thanks.
Yeah. Okay, so this kind of tells you that when you verify this condition, you can see that this particular testing design is not a feasible design. So now let's look at another design. So here you can see, again, I can do the same kind of a test of this feasibility condition. So if I take the possible defective set to be 1, 2, and 3, you can check that there is a test T1 where item 1 is before 2 and 3. There is a test T2 where item 2 is before 1 and 3. And then there is test 3 where item 3 is in fact the leader. Okay. And we can repeat this process. So for 2, 5, 7, again, it turns out that you get a test where each of these items is a leader amongst the possible set of defectives. And the same thing kind of holds true for all possible triples in this particular case. Okay, which is why this is a feasible testing design for this case of k equals 3 and n equals 7. Okay. Now, as I said, this particular feasibility condition gives us the analog of the disjunctness condition. Reconstruction in this case is quite straightforward. You just look at, because in every test, you are essentially getting the identity of a defective item. So your reconstruction is just the collection of all those defective items that you see in the outcome. That is your reconstructed set. And if your underlying testing design matrix is in fact feasible, then you would, or you are guaranteed to actually recover all the defective items. Okay, so the reconstruction is just straightforward. It is just coming directly from the outcomes themselves. Okay, now, so using this feasibility condition, we managed to show firstly an order k-square lower bound on the number of tests that are needed by any non-adaptive testing strategy. I won't go into the details here, but it's essentially using exactly this feasibility condition and arguing that for any such matrix to be feasible, it needs to have at least these many rows, at least order k-square rows. Okay. Now this actually matches with what BGT also has, right? But it is not trivial because under this cascaded model, you are actually getting more information. So this lower bound is not immediate from the Boolean testing result. We also come up with another lower bound. So one thing to note here is that this lower bound actually gives no dependence on the underlying size of the population, right? It's independent of n. We have another lower bound, which comes from this Erdos-Zekaris theorem, which gives us a lower bound of log n, essentially, on the number of tests required by any non-adaptive group testing strategy. So again, I can go into the details later if anyone is interested, but the idea and this theorem, what it gives is, it says that if you take any sequence of length a square, then it always contains a monotonic subsequence of length a. Okay? So what that kind of, if you think in terms of what our feasibility requires, as I said, it requires every item to come kind of first amongst the possible set of defectives, right? So you don't want monotonicity. So to get this lower bound, we actually exploit this theorem, which gives us that if you use fewer than log n tests, then there will in fact be a collection of k items which remain monotonic, which remain in the same order throughout all those tests. And so that means that the underlying design cannot be feasible. Okay. So again, as I said, I can go into the details of this if we have time later and if someone is interested. So this is what we have in terms of lower bounds. We have this maximum of k square and log n in terms of the lower bound. And the upper bound right now, I haven't talked about it. The upper bound is what we get directly from Boolean group testing, right? So you can see that the lower bound has this log n dependence, whereas the upper bound has a log n dependence. So there is an exponential gap between the two. And so, I mean, for us, the main question was, can we actually benefit somehow from, can we come up with explicit schemes which show that under CGT, you can go below this log n dependence. Okay. So I think I have how much time do I have?
We usually stop at 6 p.m., but yeah, you can extend maybe for 5-10 minutes. That's
No,
okay.
I think yes. So 5 more minutes.
Yeah, I think 5 minutes is good.
Okay, all right. So yeah, I'll just give you maybe a quick kind of idea about how we go about constructing and achieve a feasible scheme for under cascade group testing. So I'll stick to this special case of k equals 3 defective items. So our construction is a recursive construction. So we are going to take the feasible a particular feasible design for A items, and then we are going to use that to construct a feasible design x2 for A square items. So we are going to build from A to A square. Okay. So so I'll illustrate this via this example where we have let's say 9 items. So A square is 9 and A is 3. So the first step is we are going to partition these A square items into A disjoint sets, each with A items. So here, because A is 3 and A square is 9, so you get 3 sets, okay? And each of them has 3 items, right? Now, so we assume that we already have a feasible testing design for A items. So we have a feasible testing design for 3 items, right? Which means there are some collection of permutations over 3 items, which we know satisfies the feasibility condition for k equals 3. So to go from A to A square, I want to somehow use these permutations on A items and construct from them permutations on A square items. So let's say I have 2 permutations S1 and S2, and I do a combination of them, which is S3, which I denote by this notation here. And the S3 permutation is on A square items. Okay. So how do I create this permutation S3? So let's say S1 is 231 and S2 is 132. These are the 2 permutations. So my first step is for each of these blocks, I'm going to first apply the S2 permutation on each of them. Okay, each of these blocks only has A items. So S2 is a valid permutation on A items. So I'm going to apply that permutation on each of these blocks. Okay, so S2 is 132, which means item 1 comes first, then the third item, and then the second item. So 1, 2, 3 goes to 132, 4, 5, 6 goes to 4, 6, 5, and similarly 7, 8, 9 goes to 7, 9, 8. So that's the first step. Now I have these 3 permutations that I have gotten, H1, H2, H3. Now I'm going to use them to create a permutation of A square items. So I'm going to combine these 3 sets. And that I do by applying this permutation S1. Okay. So S1 is 231, which means this block 2 is going to come first. So 465 comes first, then the third block 798, and then the first block 132. Okay. So this is how I take permutations on A items and I create permutations on A square items. Okay. So now how do I use this this kind of mechanism? So yeah, so this S3 turns out to be a valid permutation on A square items. So what I'm going to do is I'm going to start with a feasible design for A items. So that has some, let's say, mod X1 tests. In this particular case, there are 3 items. So there are these 3 tests, and it's easy to see that this is feasible for k equals 3. My first step is I'm going to take all these tests, each individual test, and I'm going to pair them or combine them with itself, right? So T1 combined with T1, T2 combined with T2, T3 combined with T3. I do that for all the mod X1 tests. Okay, so the number of items in F is exactly mod X1. Now, my second step is that I'm going to now look at a feasible design for k minus 1 defectives. So in this particular case, k minus 1 is just 2. And we have already seen that a feasible design for k equals 2 is just the forward permutation and the reverse permutation. Okay, so this is G1 and G2, and I'm going to take all possible combinations of G1, G2 and construct this collection, another collection of permutations, which has these 4 possibilities. Okay, all possible pairs between G1 and G2. Okay. So my overall design is essentially the union of these permutations. Okay, so I take the collection of permutations that I get by taking these pairwise combinations of Ti with Ti coming from the feasible design on A items, and then I take all possible pairs of the tests coming from k minus 1 defective from a feasible design which works with k minus 1 defectives. Okay, and then I just combine all of these together. In this particular case, the combination contains 5 permutations. The remaining 2 are in fact redundant. But you can see that, so we show, first of all, that in fact this design is feasible, which means it satisfies the feasibility condition that we had, which means if you take any triple, okay, because k is 3, you take any triple, you will always find a test where each of those items comes first. So for example, if your triple was, let's say 2, 4, and 6, then this first test has 2 coming before 4 and 6. The second test has 4 coming before 6 and 2. And the third test, in fact, has 6 coming before 4 and 2. Okay, so it satisfies that feasibility condition. And we prove that, in fact, that holds for all triples. That is, that comes from how the construction has been designed. And the number of tests is, of course, the number of tests in the first part, which was mod x1, and the number of tests in the second part, which was just 4. So you get this recursive condition of mod x2 being less than equal to mod x1 plus 4. So we have this recursive design, and it if you solve this recursion, you will see that it requires at most order log n tests. Okay, and so this idea, in fact, generalizes to any constant k. I showed it for k equals 3, and in general, it requires this log n to the power ck, where ck is essentially like 2 to the k. Okay, so that is the number of tests that this design will require for any given k. Okay, so you can see that it has this log n dependence, but it also has this kind of a power which grows as 2 to the k. In any case, so of course, for some smaller values of k, this quantity, because it has a log n dependence, it can be much smaller than the constructions that you get from just Boolean group testing, which has a logarithmic dependence on n. Okay, so this is kind of the final table that we have so far. We are able to demonstrate situations where this kind of cascaded group test gives you an exponential benefit over standard binary group testing. I'll just quickly summarize. So we looked at this new variant of group testing where you get additional information of the first defective item that you encounter beyond vanilla group testing. We derived some bounds for both adaptive and non-adaptive testing, and we came up with some explicit strategies under the non-adaptive case, and also some lower bounds. There are several open directions. Firstly, even under this basic kind of zero error, all possible tests allowed kind of situation, there are still gaps between the upper and lower bounds. For if you look at any value of k, we still have our kind of achievability gives you log n to the power 2 to the k, whereas the lower bound is just log n. So there is still a lot of gap between the upper and lower bounds. And furthermore, we've just looked at like the most basic setting right now. One can look at all kinds of noisy models, plus also constrained testing. So like Siddharth was talking about, I mean, you have several applications where it doesn't make sense that all possible permutations are allowed. There are underlying constraints on the type of permutations that are allowed. That might be, for example, defined by the graph, or even you might not want to do completely adaptive or completely non-adaptive. You might want to do things in terms of phases, or even looking at instead of zero error, looking at either vanishing error or partial recovery, etc. Okay, so there are I think there are lots of open questions in this model. Yeah, with that I'll end, and I'll take any questions that might be there.
Thank you, Professor Nikhil, for an informative talk. I would request the audience to ask your questions.
Can I ask a question?
Yeah, please go ahead, sir.
So firstly, very nice talk, right? Very nicely structured. I really appreciate it, and the construction at the end was quite nice. Going back to the converse, so your K-square converse, which looked interesting. I'd have to read the paper for more detail, but it goes back to my question about separability versus disjunctness. In the classical setting, it's a separability, which basically says any subset of size K has a distinct output, right?
Yeah.
Leads to the corresponding answer. Whereas here, if I understood it, your lower bound implicitly relies on the feasibility definition you had, which is a more restrictive definition. So I'm concerned that it may not hold for like a generalized notion of separability, because the separability, all you would need is any subset of K results in somehow distinct set of test outcomes. Does that make sense?
So I think if you need, the property that we are using is that I think the idea for us is that if you have any item, so if you take any subset of K items, then each item should appear before the others, at least in one test, right? Otherwise, if you look at a possible collection of defectives where all of those items were there, versus if you remove this, one item that doesn't satisfy this property, under both these situations, you will get the same outcome.
Okay, well, like in the classical Boolean group testing, there is a connection between K-1 disjunctness and K separability, right?
Yeah.
So an analog over here, which would be nice to see to complete the picture, would be to show that for any any decoding rule you could employ, not necessarily your decoding rule, requires some analog of this feasibility condition you had, which I'm not seeing currently, right?
Okay.
Because it's tied to a specific decoding rule. Does that make sense?
I think I understand what you're saying. I'm not quite seeing it as being tied to the decoding rule. I'm just directly looking at the outcome vector that you will get if you consider if the property is not satisfied. Then the claim is that the outcome vector will be the same for two possible defective sets.
Okay, so then that sounds like a notion of like separability.
Separability, right? I see.
It's like you might be able to come up with a corresponding separability notion here as well, which is quite nice, right? Like the parallel. Okay, and the other one, maybe you already saw my email. Like it seems like the dynamics are quite different when you allow vanishing error, right? I don't necessarily want to hold everyone hostage here, but I just wanted to ask if in the vanishing error regime, do you think like order K tests are optimal, order K log K, like somewhere in?
Yeah. So, I mean, I have to say we haven't thought a lot about it, but I don't know. I think, that's definitely something I'm very interested in, and it's not something we've resolved yet. I don't even know. Yeah, I'm not sure whether it's K log K or K. So yeah, I'm really not sure whether. So we haven't been able to come up with, let's say, a strategy which can go beyond K log K. My feeling again is that, and this was true even for the zero error case. I don't think a randomized, or at least my feeling is that a randomized construction, just a symmetric randomized construction, might not get us beyond K log K.
By beyond, you mean less than K log K?
Less than K log K. Now, I mean, I don't have a lower bound which says that K log K is needed. So I'm not sure whether it's somewhere in between, or whether there is a deterministic, or let's say a less symmetric construction which can in fact get us beyond. So Yeah, that is something that is definitely open. I don't know the answer to that.
Yeah, very interesting talk. I really like the model, and yeah, nice talk.
Yeah. Thanks.
Any other questions? Okay, I guess there are no questions. So I would like to end the meeting. Thank you again for the very informative talk, and thanks everyone for attending.
Right. Thanks for the invitation. Thanks everyone. Bye. Bye, Parimal.